Hello, here we discuss the Young's double slit experiment, and this tells us the conditions for interference to happen, and the equation governing this is given by the path difference between two rays. Let me draw a diagram. So that's one of your screen. That's the second screen. That's the two slits we have, and that's the path difference of one ray, and that's a path difference, or that's a path of the two rays. And the path difference here is the difference between the two rays, which could be measured by this. So that's your path difference. And if the angle average beam forms is theta, which is identical to either one of them in the small angle approximation. So that's angle theta. You can take the angle of either one of them. And if this is distance d, we have this distance, the path difference to be d sine theta. The equation governing interference is given by the refractive index n times delta x, the path difference between the two beams, divided by the wavelength of light used, plus m prime, where m prime could be any number between 0, 1, 2, and so on, integer numbers, times half, is equal to an integer which could be again 0, 1, 2. N tells us what's the refractive index of the path difference that we have. N here is happening in air, so that's 1.0. Delta x in our problem is d sine theta. That's our path difference. And if angles are small, we can also replace it by theta as far as we read the angles in radians. Wavelength is 650 nanometers, 10 raised to minus 9 meters. M is equal to 0, 1, 2, 3, but in particular M prime is decided by the number of phase changing reflections, and there are no reflections happening. The first beam goes from here to there without reflections. Second beam goes from the second slit to the screen. So M prime is equal to 0, so no phase changing reflections. Putting this all together, we can write our equation as d sine theta over wavelength is equal to m, where m is 0. So m here I should say is 0, 1, 2, and so on. It's also possible that we could have m plus half here, and that's for destructive interference. So these are the bright fringes. So these are bright fringes, and these are dark fringes. We are in part A of the problem. The question is asking to find angle theta between 0th bright fringe and the second order dark fringe. So here we use another color. So this is the 0th bright fringe. That's +1 bright fringe. That's +2, and so on. And we have -1 here, -2 here, and these are all bright fringes. In between these, we have the dark fringes, and dark fringes is 0 plus half, so this is a 0th order. Dark fringe will be 0 plus half. So that's this dark fringe here. The second dark fringe from from 0 would be 1 plus half. The next one would be 2 plus half, and so on. Similarly, we can go below. This will be minus 1 plus half. This will be minus 2 plus half, and so on. So we can write, putting in all the numbers. So D is 0.15 millimeters. So that's into 10 raised to minus 3 divided by wavelength, which is 650 to 10 raised to minus 9 times sine of the change in the angles. So let's say this is delta theta. And here it is a difference between the 0th order and the 2nd order dark fringe. So 2nd order dark fringe would be, so that's the 1st order dark fringe, and that's the 2nd. So sorry, this is a 0th order dark fringe, 1st order dark fringe. There's a 2nd order dark fringe, that's 2 plus half. That's here. That's a dark fringe here. And minus of the 0th order bright fringe, that's just 0 itself, so minus 0. So that gives us 2.5 then. So angle in this way comes out to be equal to delta theta is equal to 2.5 times 650 into 10 raised to minus 9 divided by 0.15 into 10 raised to minus 3. And theta then, delta theta is sine inverse of that quantity, and that's equal to 2, take the inverse of that, that's 6.2 degrees. Give me a second, I think I'm messing up here. So that's 10 raised to minus 3 here. I can make it 0.650. It is 650. Having difficulty multiplying numbers. 0.650 into 10 raised to minus 6 divided by 0.15 into 10 raised to minus 3. Okay, so it's 2.5 into 65 divided by 15, and then divided further by 1000. And inverse sine of that gives us 0.62 degrees. That's an angular separation between the second order or the dark fringe and the 0th order bright fringe. So second order dark fringe would be this and this here, right? That's an angular separation here. In part B, we have a similar problem, but we look for determine the distance between the first order and the third order bright fringe. Now we are looking for the y direction. So first we look for angle. So now the equation reads d over lambda times sine theta is equal to third order bright fringe minus the first order, so 3 minus 1 basically. So it is 3 minus 1, which is 2. But we also have the angle that we have is sine theta is approximately equal to tangent theta. And then we can talk about y over distance d, where d is the distance the between the screen and the slits. So that gives us d over lambda times delta y over d is equal to delta m in a sense, which is 3 minus 1. So delta y is equal to delta m times d times lambda times small d. That's equal to 3 minus 1 times 1 meters. 1 meter, that's the distance between the screens. Lambda is 650 nanometers. So let me say 650 nanometer. That's 10 raised to minus 9 divided by 0.15 millimeter. That's 10 raised to minus 3. So that's equal to 2 into 650 divided by 0.15. And there is a 10 raised to minus 6. So that's 8.7 millimeters. That's a distance between, so if I were to draw that with blue, let's say, it is the third order bright fringe from first order bright fringe. So that's the first order bright fringe, and the third order bright fringe would be the next one. It's plus 2, 3, and that's the distance between those two fringes. Let me stop sharing at this stage and stop the recording.